Hi, I welcome you to this class on abstract algebra. So today we are going to continue our study of integral domain. In our last two classes we started the study of this integral domain and we saw definition of integral domain, and we say that integral domain is a commutative ring with identity in which there is no zero divisors. And we saw examples of integral domain. We said the ring of integers, the ring of rational numbers, the ring of real numbers, the ring of complex numbers, and the ring of integer modulo a prime, that's ZP, where P is a prime. So we saw those examples of integral domain, and we also, in our second video, we saw examples of non-integral domain. We said Zn, that is the ring of integer modulo n, where n is not a prime. We also saw the ring of 2 by 2 matrices over the real numbers. So that those two rings are not integral domain. But in this class we'll look at couples of proofs and that's couples of questions involving proofs on this integral domain. The next one we are going to consider is to prove that every field is an integral domain, which is actually true. Every field is an integral domain. So we are going to start the proof. So we just say let F be a field. Let F be a field. So if F is a field, we know the definition of a field. A field is actually a ring. It is a commutative ring with identity in which every non-zero element has a multiplicative inverse. So if F is a field, so this simply implies that F is a commutative ring with identity in which every non-zero element is invertible. So F is a field implies F is a commutative ring with identity in which every non-zero element is invertible. So it implies that every field will already satisfy commutativity and also satisfy the presence of identity. So we know that for integral domain, the ring should be commutative and should have identity. So the field has already satisfied this commutativity and the presence of identity. And also in an integral domain does not have a zero divisors. So in our last class we saw the definition of zero divisors. Assuming that R is a ring and you have that A and B is in the ring R, with A not equal to 0, B not equal to 0. So if it happens that A times B is equal to 0, then we say that A and B are zero divisors. So the definition of zero divisors is you have a ring R and you have two non-zero elements of the ring, of which if you multiply them you are getting 0. Those two elements are non-zero, and if you multiply them you are getting 0. So we say that those two elements are zero divisors. But we want to show that in a field there is no zero divisors. So the field is already commutative, it has identity. So the extra thing we have to show there is it doesn't have zero divisors. So how do we show that? So we are going to say suppose suppose that A times B is equals to 0 for A be element of our field F with A not equal to 0. So we want to show that this field F has no zero divisors. So we suppose that the product of two elements is 0. Now, for this field to have no zero divisors, if the product of two elements is 0, then one of the elements should be what? 0. One of the elements should be 0. But for definition of zero divisors, if the product of two elements is 0, it means that those two elements, they are non-zeros. They are non-zeros. But for definition of elements not being a zero divisor, is that whenever the product of those two elements is 0, then one of them must be 0. So I say, suppose that A times B is 0. Now I say with A not equal to 0. So we want to show that if we can show that B is 0, it means that this field F has no zero divisors. Because since A times B is 0 and one of them is 0, it means it has no zero divisors. But if A times B is 0 and none of them is 0, it means that that's a zero divisor. That's the definition of zero divisor. So we are going to say since F is a field and A is not 0 in F, so this implies that A inverse exists in F. So because F is a field, every non-zero element of that field F has an inverse, multiplicative inverse. So since A is in this field F and A is not 0, we know that A inverse is present in what? F. So in this, we can multiply both sides of this expression by A inverse. So multiply both sides by A inverse. So you come here and multiply both sides by A inverse. So we are going to say A inverse is multiplying AB. Then the same thing you do to this right side. Then A inverse is multiplying what? 0. So we have multiplied both sides of this expression by what? A inverse. So by associativity, I can use the associative law in this side. So we are going to have that this implies A inverse times what? A, then times B is equals to A inverse times 0 will give you what? 0. So A inverse times A is what? 1, which is the identity, multiplicative identity. So this remains 1 times B will be what? B. And this B will be equal to what? 0. So it means that in a field, if the product of two elements is 0, then one of them will be what? 0. So therefore, F has no zero divisors. It has no zero divisor. So hence F is an integral domain. So we have concluded that the field F is an integral domain because it is commutative, it has identity, and we have shown that in a field F there is no zero divisors. And this is a complete definition of an integral domain.